Ladies and gentlemen, welcome to this latest teaching session in the course on technology and the future of medicine. Today, Osmar Zaiane is giving the second teaching session on the promise and perils of artificial intelligence. Osmar, take it away.
Thank you. Well, good afternoon. So indeed, this is our second part. So I'll remind you that last week, I was making this metaphor about reverse engineering. I mentioned the example of a child breaking toys, dismantling them, not necessarily just to break them, but to understand how they work, and then they put them back together. Once they understand how these toys are put together in the first place. I also used the water flosser, and I explained the case where I've never built one of those, but if I understand how it works, I can actually build one. Okay, and I explained how. So this is just to emphasize the fact that if we want to build intelligent machines that can genuinely mimic our functions, our intelligence, and so forth, we need to reverse engineer the human body, and for that we need physicians, we need biomedical engineers, we need sociologists, philosophers, and so forth. And I highlighted the fact that we still actually don't know how the intricate functions are actually coded inside us. How this machine is intelligent, we don't know. Okay. The other message I wanted to convey last week was the fact that I see like a scale of intelligence, and it's because we are intelligence well, we're animals, we are intelligent animals. It's thanks to our intelligence and ingenuity that we succeeded on this planet, not necessarily because of our physical strength. There are many other animals that are way stronger than us. So there's this scale, and I put the humans in level 0. There's something that I call sub-intelligent, like the mouse, and I explained that the mouse is actually intelligent. And we can imagine something above the 0, so positive, in other words, more intelligent than us, and that could be the machines that we're talking about. Now, the interesting thing is that this mouse that is intelligent cannot imagine what is our intelligence, cannot think the way we do when we do abstractions with mathematical formulae and things like that. That mouse cannot understand E equals mc squared, and what does that mean? So in the same way, we cannot imagine what that intelligence, superintelligence would be. We can imagine that it might exist, but we can't describe it. We can't even describe our own intelligence. Then we talked about singularity. So this is the point where a point in time where the most intelligent thing on this planet is not the human being anymore, but something else. What is that something else? That something else will drive innovation. And because it will drive innovation at that point, we don't know, we cannot predict how it will become. Okay? It'll be recursive, self-improving, and at a very fast rate. We finished by talking about these different ways of reaching this technological singularity. One, I would say far-fetched, but one way is to accelerate the natural selection, so improving biology, basically. But that will take a very, very, very long time. I personally believe that if I take a person that lived 5,000 years ago, and if that person is born today, that child will behave exactly the same way as our children today. We have the same capacity. So we didn't evolve that much. We have way more knowledge, but that machine hasn't changed much. So to think about improving that machine biologically, it's possible, but it'll take a long time. I don't think it's the fastest path. The other path is to create a completely artificial intelligence that would eventually exceed the human intelligence. But I mentioned last time that we are doing huge strides in the hardware side, but the software side is still very slow, and we need that software to drive the hardware. Okay, and I think to make it faster, we should start building machines that can write code themselves. If the machines can write software, that'll be faster, and maybe we'll arrive that way. The third path was to merge the two. Okay, so why is it just a machine? Why is it just a natural human being? Why can't it be both together? And there's a movement that believes in that, and I'll talk about it a little bit more later on. And the fourth one, this is where we stopped last week, is the possibility of combining small entities that are not that intelligent per se individually, but combined together in a network. Something may emerge out of that could be intelligent. So we are building things like that we call the Internet of Things. There are many objects that are being connected now on the internet. Sensors getting things, cameras, computers, you name it, coffee machines, whatever. They're all connected, and together they could create something that we didn't even foresee. And I made the analogy with the ants. So one ant cannot think about the sophisticated and complex architecture of an ant's nest, yet these ants' nests are built. It's not one ant, but the collective. So the collective has this intelligence to build these big nests. Very complicated. Okay, so I changed a little bit the roadmap. Last time we talked about thinking machines and singularity. Today I'll talk a little bit more about artificial intelligence, and I'll leave the machine learning expert systems for Thursday. Who has seen these pictures? One person. This was big news last week, or the week before. So these are pictures, two pictures taken by the same robot. It's a rover sent to Mars in 2004. And for the 10th anniversary, NASA had this big event, and they were talking about the data still coming from this mission. So the mission was designed for 90 days, but since the rover was there in Mars, well, they kept on collecting data until it dies, basically. The interesting thing is, you can see here, the rover took a picture of this place, and then later took another picture of this place by accident, and NASA engineers noticed that there's something unusual here, a donut. Where does it come from? Do you notice that thing? It's exactly the same rock here, the triangular rock, it's here. And they started speculating, what is that? Where did it come from? Remember, we're going to Mars to see if there's a life form or something interesting to us. So, of course, people started speculating on how did it come by itself there? So we haven't heard about that story. Of course, some people came up with many very fancy stories, but the two plausible ones were the fact that maybe a meteorite fell not far away from there, and rocks were pushed to this position, but that was dismissed very quickly because there's no dust. Had a meteorite fell there, they would have noticed it But after a lot of investigation, they realized that actually this piece of rock was exactly here, in this corner, and the rover, the wheel of the rover, pushed it and turned it upside down. So when you see it in color, it's actually very bright red and very white compared to the color of the surface. That's why it was very puzzling. And this has to do with the fact that that rock was turned upside down for billions of years, so it didn't see the light whatsoever. So it was stuck in the tire, and it's the tire that turned it. The interesting thing here, this wasn't discovered by the rover. So had I sent a child there, between quotes, the child would have noticed, oh, gee, there was something unusual. What is that? We'll grab it and look at it. It's an instinct. Okay. Even though we programmed intelligence in this rover, and I'll talk about this intelligence when I'll talk about machine learning on Thursday, that rover wasn't intelligent enough to realize this is out of place. It was the engineers looking at the pictures that made that reasoning. This is a very important point, okay? Because I was talking about intelligent machines. If it was slightly intelligent, it would have noticed that this is not the same as what I saw before, and it shouldn't be there, it's out of place, okay? So we instinctively have this notion of context that machine didn't. Okay. So, okay, where do I stand vis-a-vis singularity? Last time I just mentioned singularity and the different paths, how to reach that, and so forth. So I'm a professor in computer science. I specialize in data mining and machine learning, so machine learning does prediction, yet I cannot predict the future. And I'm supposedly well positioned to be able to give you the right answer about singularity. Well, I will not. Basically, this singularity, this hypothetical future emergence of greater than human intelligence through these technological means, I believe it's possible, but I can't predict when it'll happen. Some people are saying, well, it'll happen in less than 50 years. I'm skeptical. I don't believe that I will see it. Maybe the next generation will, maybe. But things are going very fast, that's true. But all those that have tried to predict the future, when we reach that point, we realize that we're completely wrong. Just watch Star Trek, and then you will realize what I'm saying. So, will artificial intelligence play a role in this singularity? Definitely. That I believe, yes. If the singularity, technological singularity will happen, AI will have a huge role there. But as we will see, AI is a moving target. What we call AI today, tomorrow is not AI. AI will be something else. Okay. Now, is there a danger with the singularity? By all means, all things that we created, there's always a second usage of that, and if we are not careful, it can be dangerous for us. So we should ask the question first, if it happens, are we ready for it? What should we do in order to prevent disasters? Do we have to have some warning systems? Or create some regulations to prevent this or that from happening. If we don't start thinking about it today, it'll be too late by the time it happens, because these machines, or whatever it is, will be more intelligent than us. Okay, so we have to be ready for it. And that's why we have courses like this, so that people start thinking about it. Okay. Now, whenever we talk about singularity, many people associate it with immortality. 2 years ago, I think it was 2 years ago, that the Time magazine had this article about singularity, and they were predicting that it'll happen by 2045, so very soon. And the title of the article says, "The year man becomes immortal," because of that association between singularity and immortality. So I'll give you my take on this notion of immortality. First, I believe when we are born, our name is already on our death certificate. What is missing is just the date and the cause, the diagnostic. We will die one day. The only way to remain immortal is to have an impact on society. That's my way of seeing things. So here's a curve that you've probably seen. This is the life expectancy, how it has changed in time. If you look at the life expectancy in the 1700s, it wasn't that great. I would have been dead by then. I mean, I way past 35 years old. And you can see that it's improving. So by year 2000, the life expectancy was in the 80s. This, I'm showing here the life expectancy for women in Japan, which is the best so far. So when you look at that curve, you can easily approximate a line there, okay, and use that line to predict how it'll be in 2050 and 2100. Okay, so 2050, if we continue the same kind of slope, by 2050 the life expectancy will reach 96, and then by 2100 it'll reach 107. That's phenomenal. Okay, and it may go faster. Indeed, there are people who are doing research, and this is a paper that was published not a long time ago, and they were showing that because of progress in medicine and engineering and biomedical engineering and so forth, actually this slope will go steeper very quickly. And according to their predictions, by 2050 or 2049 in this case, the life expectancy will reach up to 125. Okay. That's interesting, especially that if you compare the different curves, I showed you the Japan, females in Japan, but if you look at in the United States, it's the same thing. Okay. Canada, it'll be the same thing as well. It's going quite fast. Here's the life expectancy for many countries, and you can see Canada is actually one of the highest in the world. We're doing quite well. But here's another point, a very interesting point. This is another research done in UK. So here they're comparing males and females, and again you can see how it's going up. Okay, life expectancy is getting better and better. But the interesting thing is that they put that curve with another curve that they call the healthy life expectancy, and you can see that the healthy life expectancy is going up, but at a smaller pace. What does that mean? It means people live longer, but with many morbidities. Okay, we're not fixing those problems. So, do we want to live longer sick? That's a very interesting question. Okay, so currently we are extending the life expectancy, but not a healthy life. An interesting question would be: can technology change that? Can technology change this trend and help us have a long life, but a long, healthy life? Okay, it's possible, yes. So we can reverse this trend and going fast. Well, not reverse it, but make it faster, so that we live like we are 30 years old. I don't know, doubt it. The other path, and this is one of the paths for the singularity that I mentioned before, is this idea of merging the humans and technology together, and this is what we call cyborgs. We have already cyborgs living among us. This is not new. It's been there for a long time. So cyborgs is the mixture of biological and artificial beings put together. Of course, this is used by many movie writers, the script writers for the science fiction movies. So there are different kinds of cyborgs. There's cyborgs where you can add mechanical devices, prostheses, to a human body. Patrick Pilarski will talk about prostheses that are intelligent prostheses, how you teach a prosthetic arm to have more natural movements and predict your movement before even you do it. So they become very, very sophisticated. But there's also the cyborg where you have a machine and you add biological cells to it. And this is not just fiction, it has been done. Unfortunately, we don't have the time, but I have a video about, and you can find it on YouTube. There's a video showing how they took cells from a rat brain and they used that as the processor to run a robot going through a maze. And what I find very fascinating is that because the cells that they used as the processor for the computer running this robot, those cells die, they don't last forever. They had to replace them with different cells from either the same rat or from another rat. And what they realized is that these robots didn't necessarily learn and behave the same way. So here you have a way of creating different robots. They look the same, but they have different personalities, which is very fascinating. So they're not just cookie cutters, they all look the same, they have their own personalities. Now, if I go back to these prostheses, now you realize what I mean by we have already cyborgs living among us. These exist. And often they are for people who lose a limb because of an accident on the farm or coming back from the battlefield. So they replace something that they lost, whether it's an eye or an arm or whatever. But I believe that more and more we'll see people choosing to replace an organ or something that they have by something artificial. Why? Because that artificial is better than what nature gave them. Okay. So that will give us a very interesting society. Of course, science fiction covered these things. Here I have the $6 Million Man and the Bionic Woman. You all watched this as kids. Well, I watched it as a kid. I don't know if you watched them. So we will all become cyborgs, often by choice. Okay, I won't go through the science fiction view because you all know it. It's actually not new. One of the early movies, color movies, in 1969, when computers just started, they already were speculating about an intelligence beyond the human intelligence. This is a computer called Colossus, built in the United States, conspiring with another computer guardian in the U.S., in USSR. And they were taking, they wanted to control the world and starting a nuclear war and things like that. So people were already thinking about the perils of this kind of artificial intelligence that is more intelligent than humans. So let's talk about these prostheses. And the question is, can machines help us design better implants? Well, I'll give you two examples that already exist, and you will realize what I mean by some people will choose to have prostheses. So the first example is a chip that is implanted on the retina, and this chip can send signals to the cells, to the optical nerve actually, to simulate something that was seen. So nothing is seen, but the signals are sent and the neurons will believe that something is seen. That chip connects to a camera that is on glasses, and the camera will then send these signals to the chip, and the chip simulates that signal on the neurons. This is for people who are blind. They lost their vision because of a degeneration of the retina. So current images that can be generated by this chip look like this. So they're very pixelized. But it's amazing because these people are blind. They see nothing, and suddenly now they see movements of pixels. And they have very limited colors. It's grayscale. But this reminds us the early digital cameras. Look at the digital cameras today. They're very, very sophisticated. So very soon, these chips will be very sophisticated, and people will be able to see in, I don't know how many megapixels, and they will be able to zoom in, zoom out, pan, without moving. So I will be able to read a newspaper 100 meters away. I can't do it with my eyes. Okay. Here's another example. This is also something that exists. You know, the cochlear implants, where the same technology as this one, it simulates the nerves here. It makes you believe there are some sounds. So there's a microphone getting the sound that exists in the environment, and then it generates the same signals so that you can hear it. Well, like when I talked about the Internet of Things, these are things. They can have an IP address, so they can be connected to the Internet. And there is an application where you talk to your cochlear implant, because it has a microphone, it can hear some commands. You can say, well, search, I don't know, about University of Alberta. And because it's connected to the internet, it can go to a search engine, find the information, and then read it to you. It'll read it to you, okay? You don't have to see it, you don't have to do anything. That's something that I can't do with my ear, okay? And those things exist already. So now the priority with implants is to help those that have disabilities, as I said, people coming back from the battlefield or injured at work or on the farm or whatever. So they lose body parts, but soon people will choose to have them. And then the question would be, what does it mean that somebody is a cyborg and this person is not a cyborg? Who is superior to the other? Should we talk about superiority and non-superiority? What about the rights? Because this person is X% cyborg, does he or she have rights like my rights? Who is the master, who is the slave? Should we even talk about being a slave or not? Because this person is 99% mechanical. So, could there be unintended consequences? So we have a goal when we add this eye to this person who lost the eye or chose to have this artificial eye. What are the consequences to that? We have to think about these things. We ought to consider these before it'll happen, because by the time it happens, it's too late. Okay. Because basically, this is the message I want to convey to you. We need to think about it. And this is happening very rapidly. So last year, IBM has an annual IBM 5 and 5 kind of event, and they publish a list of things that will have an impact in the next 5 years. And last year, they were talking about working on artificial senses, giving the senses to the 6 senses that we have, or the 5 senses that we have, giving these senses to the machines, the smell, hearing, seeing, feeling, and so forth. And they believe that in 5 years that will be possible, okay, giving multiple senses to a machine. So imagine how that will become. So it's happening very rapidly. Don't think it's in a decade or something. So I want to give you another example. In the past I showed the video, but I suspected the internet will not work properly, so I prepared it with images. This is a picture taken in Vancouver during the Stanley Cup finals. So this is a camera that exists, takes pictures, and it was installed in many places. Actually, it's in many cities. But it happened that it was in the Georgia Street in Vancouver. And a picture was taken of this crowd. Do you recognize anybody in this crowd? No. Is that a normal picture? Seems like a normal picture, doesn't it? Well, look, this actually picture was taken with a very special camera. It has 2100 megapixels. So you can zoom in. So you see that guy next to that tree? Do you recognize him? You obviously can't. So I'm going to zoom in there. Okay, do you see him? No? Well, I can zoom in even further. There he is. I can zoom in even further. So that's what I'm talking about when I say that some artificial eyes will be able to do that. Wouldn't you like to have an eye like that? Yes? No? You don't care? If everybody has that, I can tell you that if 1 million people install this kind of eye and they don't have any problem, I'll be the first in line asking for one like that. That's amazing capability. It'll happen faster than you think. Okay. This is a typical resolution. This is with a camera like 20 megapixels that we have. Had I zoomed in this place, this is what I would see. Nothing. But a very high resolution camera, this is what I can see. Okay? That gives you an idea about the capabilities that we will have very soon with these artificial eyes and whatever. Okay. So also I have a video, but because of lack of time, I will not show it. This is there's a URL here. You can go and look at it in YouTube. This is DARPA that revealed one technology that they installed in drones. So these planes that can fly without a pilot on board for surveillance. So this is a camera built with 360 normal cameras from cell phones. So cameras like this, they put 360 cameras one next to the other. And with this artificial eye now on the drone, they are able to see not just that picture that I showed you, way beyond that. From 9 kilometers up there, they can see a bird flying, or they can see a pack of cigarettes on the floor. And they can track all the objects that are moving at the same time. And they were saying in the documentary that they would need 3 drones like that to track every single person in Manhattan at the same time. Okay, so that's the kind of capabilities very soon we'll reach. I mean, we can't fathom it. It's phenomenal. Okay. So basically, the future is already here. It is just not evenly distributed. This is a famous quote. Okay. So what is artificial intelligence? It has been defined by different people. Some people consider it a set of tools. Here, if I go to the UNESCO definition, UNESCO education definition, it's a set of tools that exhibit human intelligence and behavior, including self-learning, robots, so the robots that learn by themselves, expert systems, voice recognition, natural and automated translation, and so forth. So they try to define it using examples. I personally don't like this kind of definition, because if you use these examples, very soon these examples that we call, for example, expert systems, they're not that intelligent anymore tomorrow, because we'll have other things that are more complex, and I'll get back to that. Wikipedia defines it as the branch of computer science dealing with the reproduction or mimicking of human-level thought in computers. Okay, so we're talking about mimicking. We're not doing exactly like them. We copy them. It is the essential quality of a machine which thinks in a manner similar to or in the same general level as a human being. And finally, another one is the branch of computer science that deals with writing computer programs that can solve problems creatively, whatever that creatively means. Okay, so if we try to define artificial intelligence, the first thing we have to define is actually, what is intelligence? What do you consider intelligent? Any volunteers here? What is intelligent?
To me, it's like being able to look at your surroundings and be able to solve any problems that may arise just based off what you have. So problem-solving skills, essentially. Problem
solving, and I like looking at your surroundings. Actually, that's very important. So, for example, that rover in Mars, looking at the surrounding, the rock is there, and they didn't even notice it. Okay, very important. Yes. Other.
Mine's sort of in his line of thought. It's more adaptability in all conditions. An intelligent being would be able to think through problems and maybe even issues. Like if there's a social group of robots, let's say, like they can solve, they can recognize there's some like social issues between them. There's a lot of behaviors that range from like simple psychology to sociology and all that stuff combined.
Okay. Another attempt? Good, thank you. Well, For me, intelligence is the ability to acquire and apply knowledge and skills. So you learn, you acquire knowledge, you learn, and you apply what you learned. The child learns seeing the parents and the environment. You look at the environment and you touch it, you smell it. The kids put them in their mouths and feel it, and then they learn from there. But they don't just learn, they apply that learning afterwards. So intelligence involves the ability to reason. You were mentioning that, so reason is problem solving. Plan, solve problems, think abstractly, so you're doing this abstraction. Comprehend complex ideas and learn quickly and learn from experience. So it's basically the ability to adapt. You adapt to the environment. You look at the environment, as you were saying, and then as the environment changes, you adapt to it. How do you adapt to it? Based on what you learned before. You apply what you learned. Okay. Marvin Minsky is one of the pioneers in this field called artificial intelligence, defined it as the science of making machines do things that would require intelligence if done by men. Or by humans, I would say, but he said men. Okay. In reality, artificial intelligence is a moving target, as I mentioned before. So I'll take the example of the shift from typewriters to word processors. So I don't know if you've ever used a typewriter. I did. You reach the end of the line, you press, goes to the next line, and so forth. If you needed to do justification, for example, justify to the left or to the right, or perfectly justify, you have to count how many words you have, how many characters you have in the line, and put enough spaces between the words to hopefully get a justified line. It was a complicated thing. And now you have a word processor that can do it automatically. Oh, man, that's intelligent. People believed it. That was incredibly intelligent. Not only it justifies the lines, but now it'll tell you, hey, this word is actually misspelled. The typewriter couldn't do that for me, but that machine now, intelligent machine, is doing it for me. That was perceived as intelligent in the beginning. Now, who thinks that a word processor is intelligent? It's ridiculous. It's not. That's not intelligent whatsoever. It's the same thing with other programs. If you think about Watson, and we'll get to Watson later, who knows about Watson, the IBM Watson program that beats the Jeopardy champion? Humans. Okay, a few of you. So that machine is incredibly intelligent. It can answer these questions very rapidly, faster than any human being. I can tell you, in less than a few years, you will realize that that's not intelligent at all. I know how it's done, so I know it's not that intelligent. But it exhibits some intelligent behavior. It is fascinating, indeed, how they manage to. It's a huge feat, but it's not intelligent. So what is intelligent, the artificial intelligence, it's a moving target. It'll change. When we solve something, it's not a big deal anymore. There are other more complex problems that we have to solve. Artificial intelligence has two goals. First goal is to build these computers that are intelligent, or at least act intelligently. But the second goal is also to understand the human intelligence. Because, as I said, we need to reverse engineer this human body in order to create something like it, or at least that mimics it. And in the exercise of building these intelligent machines, we are trying to also understand how we function. Okay. And that's why we need not only computer scientists, but also psychologists, philosophers, linguists, and so forth. So, oh man, have to be way faster than what I'm doing. So the term artificial intelligence was created in the 50s, in 1955 exactly. So a group of people who were working on intelligent machines, led by John McCarthy, organized a conference in Dartmouth, in the East Coast. And they wrote a proposal in 1955 to organize this conference in 1956. And in that proposal, McCarthy suggested this term, artificial intelligence. And they were very, very optimistic. So they thought that now we have these computers that were able to calculate very rapidly compared to what we can do. We will solve this problem of artificial intelligence. We will build these machines. Unfortunately, that wasn't realistic. However, the field of artificial intelligence per se was created after this conference, and now every single computer science department in the world teaches artificial intelligence. It's becoming a field in itself. Okay, that's the legacy from here. But yeah, what I wanted to say here. I prefer calling it computational intelligence more than artificial intelligence because I don't like the term artificial. It's not really artificial. It's just an intelligence that is computed. You calculate it, you compute something. It's processed. And with computers, we can build this capacity to observe, interpret that environment, as you mentioned, what surrounds us, and adapt to it. And I'll mention that in machine learning. So we will have the ability to learn from past experiences and then apply those learnings in the new environment. So since we can compute that, that's the what I define as computational intelligence. Okay, so it's the whole question is about adaptation, adapting to the environment. The environment could be like the robot in Mars, an environment that nobody ever saw. We haven't been there. We're sending this machine in a place that we don't know, so obviously it has to adapt. But it can be also a program that adapts to data coming in. Okay, that data could be information about patients, like it can be data coming from the stock market. We can adapt to these changes, and I'll mention that in machine learning. So we are faced with serious problems to do this artificial intelligence or computational intelligence. First one is that the human intelligence per se is not completely understood. We don't know how really it works. We are speculating, and we have different hypotheses and so forth. And even if we understand the human intelligence, we can't comprehend an intelligence superior to us. We don't know what it is. It might exist, yeah. We can think it could exist, but we can't describe it. We don't know what it is. We're not intelligent enough to be able to describe it. Now, there is also what we call a weak AI and strong AI. The weak artificial intelligence refers to AI that only simulates the human thoughts, okay, and actions. And all current AI that we have around us are weak AI, and I'll give many examples. There's the strong AI, which refers to intelligence that can match or exceed the human intelligence, and that we haven't reached yet. So it's not just a simulation, we're mimicking the intelligence, we're actually creating a real, true intelligence. Now, to try to define it, people have talked about acting like a human or acting humanly, since we cannot define it. And one famous test to demonstrate that a machine is intelligent or not is what we call the Turing test. So Alan Turing is a mathematician who actually was one of the pioneers even in thinking about a science called computer science, in a paper that he wrote in 1936. So he's the father, some people call him the father of computer science. He was instrumental during the Second World War, building machines that can decipher the codes from the Germans. And working so closely to the machines, especially after the first real computer was created and released, ENIAC, in 1946, after the Second World War. Everybody was talking about these computers. Him being a mathematician, he was trying to think about how these machines could eventually think. And he wrote an article in 1950 about thinking machines. And trying to define thinking and thoughts, he said, okay, let's put it aside. and consider now how to compare a machine. When do we say that a machine is actually thinking? Even if we don't know how to define thinking, when can we say that a machine is actually thinking? And he devised a game. This game that we call today the Turing test is based on a Victorian game, a very old game, where the Victorian game was to have two people behind a curtain, and they pass you these messages, and you write messages, you pass them another message, you don't talk, you just send messages, and you have to guess if the person behind the curtain is a female or male. So he used that idea, this game, the Victorian game, and he created his own game called the imitation game. And in this case, you have a judge in one room, and you have two other rooms, where one you have a computer, the other one you have a human being, and they are having a conversation with terminals, via terminals, with this judge. And if the judge doesn't know where's the machine, where's the human, then that machine is intelligent enough to fool the judge to believe that that's a human being. Okay, does it make sense? Okay, that's called the Turing test. Now, the interesting thing, in 1950, he died in 1952 or 54. In 1950, he predicted that by year 2000, so we passed already, he said by year 2000, a machine might have 30% chance of fooling a layperson for 5 minutes. So he insisted on this 5 minutes. This shows how difficult this task is. It's a very difficult problem. And he said if the machine can do that for 5 minutes, and it fools 30% of the judges, it means that that machine is intelligent. Okay. I can tell you, we're in 2014, we haven't reached that yet. Okay. It's a very hard problem. But even if we reach that, so actually, I believe last year there was a machine that was fooling the judges 29-point-something% of the times within 5 minutes. So we're very close. But even if we do that, if we manage to fool people, is that really intelligence? So many people are debating this. Was Turing right about this test? Many people don't believe that. Because many of these tests are actually based on tricks to fool the person. I can tell you that, and I'll show you the example of the winner that reached 29-point-something%, Eugene. Eugene, the trick that they used, among other tricks, is to pretend to be a 13-year-old boy from Ukraine. So, because you can guess some of the machines when they do mistakes, but because it's a boy and from Ukraine, you allow those kinds of mistakes. And then, as a judge, you're fooled. Anyways, very early on in 1966, people were building these chatterbots. We call them chatterbots because they can have a discussion with you, a dialogue. Some were very sophisticated, but of course, far away from beating the Turing test. But a few years ago, there was an inventor, Hugh Lobner, who created this prize, an award of $100,000, the first computer that can beat the Turing test. And many people wanted to get that money, of course, so they built many, many chatterbots. And this one-time test became an annual competition, and every single year we have this a set of new chatterbots that are trying to fool humans. So I'll show you examples. Here's a conversation with Jabberwocky, one of these chatterbots. It got the third place at the Lobner Prize in 2003 and the fourth place in 2008. You can go to this URL and test it. I'll show you here an example. So Jabberwocky is asking, what's your name? And I say, Fred. He says, no, it isn't. Wow, how did he know? And I say, do you mean I'm lying? And he replies, or it replies, yes, I'm a very good liar. one of the best, but I was talking about myself being a liar, and he says, I'm a liar. So, and I said, that doesn't mean that I'm a liar if you are a good one. And says, yes, it does. Why is that? I am God. So immediately you realize this is silly, and I was joking continuously. Well, do you have a temple for you? No, that's all right. And then, so you're God with a small g, because he wrote it this way. And then I am small g. So you realize that it cannot follow the discussion. It forgets actually what it said before, and when it's stuck, it generates silly things. It's very easy to realize it's not a human. Okay, here's another one. This is Alice. And Alice won the Loebner Prize many times. 2001, 2002, 2005. In 2008, they were fifth, because there are other ones that became even better. But here's another conversation. So Alice says, I'm Alice. And I say, where are you? Oops, I'll put the whole thing. I'm in Auckland, California. And he's asking me, where are you? In Canada. Tell me a little bit about Canada. And wrote it in small. And I said, it is cold. He said, I am warm here. Where's the best China restaurant? I ask it. And he says, I think it's a Thai. Why is it a Thai? So this response has absolutely nothing to do with that question. And he says, why do I exist? To test artificial intelligence. What's the sound of, it's talking about clapping with one hand. It has absolutely nothing to do. So it went to a different tangent. And you realize this cannot be a human. Here's another example with another very famous chatterbot. It's famous because not only it was a finalist many times, but because it's free, people can download it and use it and integrate it with their own tools. It's called Cleverbot. And again, when you look at the conversation here, it becomes silly very, very quickly. This is Eugene. Eugene won a few times, but at the last Loebner Prize, it got 29 point something %, which is very, very good. And here's an example of the conversation. I'll leave you the slides. And you see how it is making some mistakes and it's pretending to be this child. So they create this context. Their context is, I'm a boy, 13-year-old boy, and I'm from Ukraine, so my English is not that great. And because I'm only a young teen, I can make silly things, basically. But you can realize at one point it's lying. It's lying because it forgets what it said before. The context is always the last question, the last answer. Okay? So these chatterbots are actually becoming very, very ubiquitous. You've all heard of Siri on the iPhones. There are also other applications on the Android, Iris, one of them. And they're becoming amazingly sophisticated. But they have a purpose. The purpose is to understand commands to access the functionalities of this machine or to retrieve information from a search engine. You cannot go beyond that. You cannot talk about politics or religion or whatever. It'll tell you, here's a web page, boom. Okay. So we're still far away from that real Turing test. The interesting thing is that intelligence is not human, only human. There are other forms of intelligence that are not necessarily human. I was talking about the mouse. Well, the mouse, we can link it to our kind of intelligence. But there are many kinds of intelligence. I mentioned, for example, the ants. That's incredibly intelligent, the way they build the nests. So when we try to define intelligence, we shouldn't just look at humans. We should look at other forms. And who's to say that the human intelligence is the best? Maybe there are other forms that are actually better than ours. And maybe that's what we should target when we are thinking about intelligent machines or thinking machines. But the interesting observation here is that humans are general purpose intelligent machines. You can talk about building a car and then talking about religion and politics, philosophy, and then talk about geography, and then talking about recipes, cooking something. It's intelligent in all sorts of things. While machines, the current intelligent machines that we have today, are very specific. They're good at one thing, and they're very, very specific. So let's look at some of these achievements that we have that are very, very specific. Very, very specific. Like we have Deep Blue, an intelligent machine for playing chess, and it can beat the best humans. Nobody can beat Deep Blue. So it's very intelligent. You have to be intelligent to play chess. But you can't ask Deep Blue to build a car or to manipulate a rover on Mars, what to do if you find a rock or whatever. Well, you could recode it, but it's specifically designed for one task, and it does amazing things. Here in Alberta, and I believe Jonathan Schaefer will also talk in this course. Jonathan Schaefer led a team to build Chinook, and Chinook is the only computer game that actually beat a human being in a tournament. So it wasn't just a show like in Deep Blue. IBM gave $1 million as a challenge. But Chinook actually won the best human in a real competition. That's an incredible feat. But there are many other things, like I mentioned Jeopardy, so Watson beat the best humans. There are other achievements that very few people heard of, but they exist, they're real, and they will come on the market very soon. These are, for example, intelligent cars that can drive themselves without a driver. And they recognize what is a pedestrian, what is a sign, there's a turn here, another car, and so forth. And this is not new because already in '95, there was this incredible challenge to cross the United States from coast to coast without a driver, okay? And that was achieved. DARPA also created this challenge a few years in a row to get the best team that can create a car that can go in a particular path without any driver. You probably heard of the Google car. So there's a car built by Google that can drive without any driver, drive by itself. And we had Sebastian Thrun, the head of that team, who came to the University of Alberta and gave us a talk about it. So there are many cars that are intelligent today. Some use intelligence without any artificial intelligence per se. They have sensors to recognize a car in front of it, or when you back, it has a sensor that tells you, oh, you're close to a tree, or you're close to another car, or whatever. You have intelligent parking assistance system, so a system that, well, you're in the car, you press a button, and the car will park itself, okay, parallel parking. You have cars that will brake automatically. If you're going fast and there's a car in front of you, it will brake without you pressing the pedal. There are cars that will tell you that there's something in the blind spot. So many of these gadgets that were added in cars, and you can buy a car with all these gadgets today. There's some gadgets that use real artificial intelligence. For example, there is a feature that recognizes the lane in the highway, for example, or on the edge of the road. And when you're trying to cross it, it'll tell you, watch out, you're too close, you're crossing it. Why there is an AI in it? Because it has to recognize that that's a lane indeed and not, I mean, there's a paint and not something else and give you false alarms. So it learns to recognize the different ones. But there are other ones that recognize, for example, pedestrians at night. Anyways, I won't go into the details, but there are many more sophisticated systems that are being added to everyday cars, and you will be able to buy them, well, you can buy them today, actually. Even systems that can recognize the different signs. This is the speed limit, oops, you are going too fast, it'll give you that warning. It'll read it automatically and tell you that, and can communicate with you. So driverless cars are becoming a reality, okay? I gave an example. Again, I don't have the I don't want to go through the video, but it's not only on the roads, but people are using these automated cars in mines, for example. And they demonstrated that the driverless trucks require less maintenance because they don't break too often. They go the right speed, they avoid the right potholes and things like that. So they require actually less maintenance. I want to give you some more time to ask questions, so I'll skip here. So why computational intelligence is important? It's becoming important because, we want to build all these machines that will help us improve our quality of life and hopefully one day build a machine that is more intelligent than us, and also to help us improve our quality of life. But also computational intelligence is important, as I said before, because we need to better understand how we function, the complexity of our human body. Okay. Oh, this is something I said before. I'll skip it, and I'll stop here. Thank you for your attention. And this time, at least, I left some so a few minutes for questioning.
Yeah. You know, when you think about the gender issues here, the very few women in computer science, when we think about the impact of AI on the future, it seems to me that these are things that like every woman would be interested in, right? I mean, every man too, but they don't seem like things that are particularly male gendered interests. So what do you think about that? Don't you think as a part of the evolution of everything else that eventually women will be more interested in training in this area, that'll become more co-equal? Or what's your take on why there's so few women in the field now?
This discrepancy, well, the difference, well, the fact that there are very few women in computer science in North America is not well understood.
Mm-hmm.
People speculated on the reasons.
Yeah.
I can tell you that it is very specific to industrialized worlds, so countries. So
Mm-hmm.
the United States, Canada, Europe in general. If you go to other countries, it's not the case.
Yeah.
If you go to Asia, for example, in computer science, you have as many girls as boys. I've been to the Middle East, same thing.
Yeah.
In Africa, same thing.
So
Here,
it's some
I don't
sort
know
of artifact of our society.
Yes, yeah.
Yeah, but
Can I just comment on that?
Sure.
Because the fact that there might be less women in computer sciences in North America, especially, could be due to some stereotypes. Maybe, like perhaps we see a lot of It could be due to some stereotypes. We see a lot of pop culture where shows portray like computer scientists as this geeky kid who wears glasses, doesn't really look that attractive, I guess, and maybe perhaps females see this and it's sort of a turn off, like they don't want to live this kind of life, right? It seems like computer science might entail sort of that sort of lifestyle. I do have a question for you though, about how software is lagging behind the hardware in terms of developing AI. Like, what kind of changes do you think are necessary to get that software to the level of the hardware so that we might see the singularity one day?
That's a very interesting question. I wished I had the answer to that. It is, well, hardware can evolve by changing the scale, for example. You can cram more transistors in less space. That's one way of improving, for example, hardware. It's not the same process for software. Software, we have to write it. And it takes way more time, and you can't copy it again and again. I mean, you can reuse software, but it's not the same way as you can scale for hardware. We have to also not just write it, we have to think about a way to write it. The computer, so I take a computer like that, and I wanted to make something, I have to tell it. And then how do I tell it? I have to express the process to go through in order to achieve what I'm asking it to do. So I have to express every single thing in that software. That's why I mentioned the best way to improve the speed at which we are going forward for software. We have to make machines write the code. If you leave just the humans, you leave this task to the humans, it'll take forever. It'll take a long, long time. Unless we have a breakthrough somewhere else where, see, people are thinking about different ways of expressing what we want the machine to do. So there's what we call declarative languages, and there are procedural languages. Procedural languages, you tell the process, the procedure, how to do things. Declarative languages, you just declare what you want to obtain at the end, and you let the machine find its way. So we have to come up with a paradigm to express what we want in software for the machine to do it. It'll take time. You cannot really do the parallel between hardware and software, how they evolve. They're completely different things.
Just sort of speaking off of that, so to get to the point where AI or computers are creating their own programs kind of independent of human input, I guess my question is, how important do you think explicit self-awareness on the computer's part is? Like, do you see it as long as they're complex enough and intelligent enough, that will be enough to create their own programs? Or do you think they need some sort of existential, like, human aspect of self-awareness?
That becomes a philosophical question. No, so there are ways of improving a program by improving the knowledge stored in the program. So I'll talk about expert systems and how expert systems work next time, and then you can understand how actually there is some knowledge and I can improve that knowledge. But how to deal with that knowledge, that stays static. It's the same thing. It doesn't improve. So we have ways to let the machine improve its own knowledge. But we don't have ways to make the machine improve the way it deals with that knowledge. We're getting there. Even machine learning is helping to do that. So for example, I can tell a machine how to recognize recognize cancer in an image, medical image. I cannot program the exact coordinates for every single image where the cancer is. Because if I do that, the day I show another image, the cancer is in another place, the program will not work. So the program has to be adaptive. It adapts to the new images that I will show. But again, it's not programming the process. Programming the process is not done automatically yet. Now, do you need self-consciousness to be able to do that? Not necessarily. The machine doesn't have to know that it is a machine and it has this capacity. I have to program in it a way to make it change its own code. So self-correcting, for example, or I may imagine I make mistakes telling it what to do, and that machine realizes, whatever realize means, realizes that that's not the best way to do it, and it improves its own way to solve that problem. That's what I'm talking about when I say coding. The machine codes its own code. No.
I feel I stole the microphone from you. Do you have a question to follow up on that response? No? Okay. So my comment, I think, is more of a comment than anything. It's also a question to everyone else in the class. And it is relevant, just bear with me. So it ties together intelligence and when we're talking about, for awareness, whether or not, since culture is the sum of a grand number of individuals' intelligence, whether or not we can expect a culture to evolve from an artificial intelligence point of view. Is it going to be a single computer or being that's in charge of a whole bunch of other little things, like continue programming at the will of this one thing that's so intelligent that we don't know where it's going? Or is it going to be do you think that it's going to be a multitude of tiny little self-evolutions, in a sense, that bring us to a place where we don't know where we're going to go?
Well, if you look at those ants, I'll go back to that. I'm fascinated by those ants, because who tells each individual ant what to do such that the collective realizes what they did? I really don't know. They send messages to themselves. I know we have a proof that when an ant finds, for example, a dead insect, it sends messages, pheromones or whatever, there's a chemical message sent to call the other ants to come and help. So they communicate. But do they use the same mechanism when it comes to realizing a big thing like building the nest? I don't know, but still I see an intelligence to design all that thing. It's possible that with many different objects communicating with each other, so now I'm going back to the Internet of Things. Rather than ants, I have objects. They can be computers, they can be cameras, they can be whatever. The eye that I have here, the sensors is on the tree, the handle of that door, the light in my room. If all these communicate together and they individually don't have intelligence, they're very, very, very specific, but they send that information to a collective somewhere, that collective may have a kind of intelligence that we still don't comprehend. And I think that can, because if I had, and I don't have that capacity, but if as a human being, I have the capacity to access all that information that is collected by all the sensors, all the cameras, and I have the capacity to process it, would I be more intelligent? I don't know. But if a machine would have that capacity, because now we're building that capacity, we're connecting everything, and we have these machines can store and can access that information very fast, very rapidly, and they can process it. Would that create an intelligence? That's the fourth path that I was mentioning. By the way, I am not excluding these paths. They're not completely independent from each other. They can happen together. So, for example, the cyborgs, which is one of those paths, they have mechanical devices on them, but those are sensors that are also communicating with other bits and pieces somewhere else. So this reminds us the story of the Borgs in Star Trek. So the Borgs are a collective. When one Borg thinks something, the collective knows about it. When one Borg experiences something, the collective knows about it. And that's why they are an intelligent race, because when they invade people, they assimilate them and they take all their knowledge, their culture and everything, and it becomes part of the collective. Now we're building a collective with these Internet of Things. Would that create an intelligence? It's possible. Is that the intelligence that we are talking about, being more intelligent than us? It's possible. Again, I don't know. Nobody knows.
I just have a question about how we might be able to create the software. Do we have to understand kind of how we have that sort of abstract thought in order to then produce? So then if we understand our own process of understanding some sort of abstraction, then we can go and create the software, or
Yes.
is it? Okay.
Yes, that's exactly it. So if I understand how I function, I will create a model and then implement that model in the machine by coding it. And then hope that that model is actually a good copy of my interpretation of my intelligence and reproduce it in the machine. That's what so the software is basically implementing the model that I create representing my intelligence. I don't know if I'm answering your question. The limit here is the ways I have at my disposal to express that model, so the language that the machine understands, they are limited. They may not be able to express exactly the model that I put on paper.
Hasn't surveillance become a really intriguing numbers problem? Because just looking at the pictures that you showed, you said that with 3 drones you could follow everybody in New York City. How many trusted NSA employees are there to check all this data out? Well, that's obviously where the shortage is. So the AI has to not only be in the drones, but also in the, analyzing end.
Definitely.
And so you end up, most of us are probably afraid of, human beings in the NSA or something comparable looking at our data, whereas the likelihood is that a sentient machine, maybe a very smart one, will be looking at our data, and only if we look really interesting in some way will a human being, be, alerted. Well, look at this guy,
Oh, definitely. So
Yeah.
currently we have these images, we have the
Right.
means to capture these pictures and listen to what is happening online or on telephones and all that stuff, but
Right.
we are reactive. We wait for an event to happen. Like, for example, in Vancouver, there was a riot. So after
Yes.
the riot, now we want to go and look for evidence.
Right.
So humans will go and look for something.
Right,
So we react to an event that happened.
right.
If we want to be proactive, then we have to look at every single person in that crowd. It's impossible for humans.
Yeah.
You need machines to do that. And you need AI to do this.
And there's a
kind of work.
basic strategy of how many people to trust and how many, machines to trust, right? I mean, if this data is so valuable, so sensitive, then at some point you have an option. Recruit a lot more human beings that somehow you feel you can trust, or make the AI much better so that you don't need a lot. But
You still have to trust the human who programmed that AI
Yes.
in that machine.
But it comes down to this 85 people that Earl Waugh was talking about, that 85 people control, a substantial amount of the wealth in the world. Well, it could be a similar number who actually control most of, the information, surveilled.
There could be less than 85.
Yeah, yes, I know, it's really scary to think about. Okay, well, we're out of time. Thank you very much
Thank you.
for an outstanding session.